Welcome to Ask and Learn.
So in part A, they want us to show for a poset there is exactly one maximal element given there is a greatest element. So let's go ahead and see what we can do. So I'm going to call the poset s less than or equal to. All right, so proof. So first assume that s less than or equal to is a poset. All right, so now let's think about what we want to do next. Well, I would say most of the time when there is something saying you want to show there is exactly one of something, you should do it by way of contradiction and assume there is at least two. And so that will usually be the right path, or at least the path of least resistance normally to show this. All right. So now we should tell the reader we're doing this by way of contradiction. So that BWOC just means by way of contradiction. So assume that is a poset. Now by way of contradiction, assume that there are, so our contradiction that we're going to want is there is at least two elements. So, or what we're going to put here is there are at least two maximal elements and a greatest element. Okay. So let's go ahead and define what these are. So if it's a greatest element, it's definitely maximal. So let's just do two of these. So let x, y be two, or actually, so I'll say first let x be our greatest element and y a maximal element with x not equal to y. All right, so now let's draw a Haas diagram out to maybe give us some inspiration on what to do. So if x is our greatest element, that means it would be at the very top of this. So like, let's say we have y, z, I don't know, a, b, c, d, something kind of like this. And then the Haas diagram just kind of has like this thing going on. So if x is maximal, this means everything should be dividing or be larger. Let me try that again. If x is our greatest element, then everything in the set should be less than or equal to this. But over here, we said this is maximal. So nothing should be larger than this element. And so this is where our contradiction is going to come up. Because we're assuming over here that x is not equal to y. All right, so let's see. So let x be our greatest element and y be a maximal element with x not equal to y. All right. Now the next thing we're going to do is since x is our greatest element, then x should be larger than everything. So x should be larger than or equal to y by definition. But by definition of y being maximal, y should not have anything larger than it. Y should not have anything larger than it. So now this right here is our contradiction. So then this implies that y is not maximal. So at this point, so we've shown it for y. Then we can repeat this for any other ones that we're going to have that are supposedly maximal. So now repeat this for all other supposed maximal elements. And you come to the same conclusion. Thus, there is only one maximal element, and this is namely going to be our greatest element, x. So now you can put your little proof box and a smiley face because you're glad you're done with it. All right. Now for this next one, it's going to be the exact same logic. The only difference is instead of saying maximal, we're saying minimal. Instead of greatest, we're saying least. And instead of x being on the right here is going to be on the left. Okay, so let's go ahead and do this. So actually, if you just copy and paste what we did over here, over there, and then, like I said again, just change out the, so like you would move x to the left and y to the right, you'll end up with the same thing. So let's go ahead and see what we get though. So let's just write it out again. So we're going to assume that S with this ordering is a poset. Now, by way of contradiction, we assume that there are at least two minimal elements and a least element. So now, at this point, we wanted to define these. So let x be our least element and y a minimal element with x not equal to y. So now the next thing we said is since y is our least element, then it must be the case that x is less than or equal to y by definition. But by definition of y being minimal, y should not have anything smaller than itself. And so then this is our contradiction again. And so that's just a symbol I use for contradiction. I don't remember if I said that earlier. You may use something different, but that's just the one I've always used. All right, now this implies that y is not minimal. Now we repeat this for all other supposed minimal elements and arrive at the same contradiction. And thus, there is only one minimal element, and namely it is our least element, x. And then again, you can put your proof box and a smiley face because you're glad you're done with it.